if a single charge that's moving creates a magnetic field, then a whole bunch of charges that are moving should also create magnetic fields. So our wire, for example, this little wire here, if we flow current through it, that wire is going to have a whole bunch of moving charges, and those charges are going to create a magnetic field, which in turn is why it interacted with this bar magnet. Okay? So the magnetic field due to a current carrying wire So the wire itself may not be magnetized, but once we flow current through it, it will create a magnetic field. The equation is actually derived from here. Remember, velocity is simply the derivative of our displacement with respect to time. What we do in our equation to talk about current rather than just a single charge moving with some velocity, Q times ds dt, charge per time is current. So what we do for our equation, we still have the mu naught and the 4 pi. Instead of Q times V, we're going to take I, the current, times ds, some little piece of the current. And then the rest is the same. We're crossing it with the r hat vector, the little unit vector that's describing the direction. R squared is the distance away. Now, similar to electric fields, we need to sum the contributions from each piece of the wire to the magnetic field at a given point. But the direction is similar to what we did with the single charge. Remember, by definition, current is just defined as the flow of positive charges. Even though the positive charges don't move, the electrons are the ones that are moving. Electrons moving down are equivalent to protons moving up. ds is going to be the direction the current is flowing. R hat is the direction pointing out towards the point we're interested in. So in terms of direction, if current's flowing up, just like our positive charge was moving to the top of the board, the magnetic field over here will be into the board. The magnetic field over here will be out of the board. The magnetic field around our wire is going to make circles. If we look at the wire as if the current was flowing towards us, then the magnetic field makes counterclockwise circles around that wire.
So what's moving in a positive direction?
Depends upon your definition of positive.
Positive is normally counterclockwise, I thought.
Well, it depends upon your coordinate system you're choosing. There's actually a second right-hand rule that boils down out of this. So we have one right-hand rule for cross products. It works for any cross product equation at all. That's where you put your index finger in the direction of the first vector, your thumb, you're out of your palm for the second, and your thumb is the result. Second right-hand rule, since we know the magnetic field is going to be circles around the wire, turns out if you put your thumb in the direction of the current, your fingers show you which way around. Imagine your fingers being arrows. Your fingers show you which way around your thumb the magnetic field will circle. So if the current's coming out at you, the magnetic field will be counterclockwise circles. If the current's flowing away from you, the magnetic field will be clockwise circles. Okay, so we're going to use this equation. By the way, if you care, it's called the Biot-Savart Law. going to use this equation to derive the magnetic field around a few different objects. For example, a long straight wire. We're going to look at, say, curved segments of wire, because it's common to have wires that are wrapped in circles. We don't really have time to do that today, so we will not do that at this moment. We'll do it tomorrow. We introduced, this is called the Biot-Savart Law. It is the equation that will allow us to find the magnetic field around any current carrying wire. So, for example, let's derive the equation for a long straight wire. We'll say it's carrying current I towards the top of the board. And let's say we want to know the magnetic field strength at a distance of some A perpendicularly from the wire. So what we need to do is we need to look at little segments of this wire, little DS's, infinitesimally small pieces, and figure out their contribution to the magnetic field at that point. So I'm going to put it in a coordinate system where the wire is the y-axis, and then I'm going to put the x-axis so it goes through that point we're interested in. So if I pick a little piece of the wire here, the length of it will be dy. ds represents the length of the little piece of wire. So ds is dy. Now vector-wise, the direction of ds is the direction that the current is flowing in. So the direction of ds is straight upwards towards the top of the board. Now similarly to the electric fields, the r in the denominator there, the r squared, r represents the distance from this piece of the wire out to where the point is located, the point that we're interested in. So we can write r in terms of A and y being the distance from the origin down to that piece of the wire. So r will be the square root of a squared plus y squared. Now a being a constant, just representing how far away we are from the wire, perpendicular distance. Y is going to be changing. It's a variable. Y is changing as we look at different pieces of the wire. So in our equation over here, we have the quantity ds crossed with r hat. If you remember, the cross product multiplies perpendicular components. Now r hat is the unit vector, meaning it has a length of 1. It's the unit vector that points from the piece of wire towards that point we're interested in.
What's that other box next to the piece of wire?
There isn't another box. There's an arrow showing the ds is upwards.
Oh, okay.
If you remember with cross products, the magnitude of the cross product can be found by taking the magnitude of your individual vectors times the sine of the angle between the two. R hat sine of theta, if we use this theta, if we use the angle between the ds and the r hat sine of theta is going to give us that perpendicular component, the component that points away from the wire. So our equation, the magnitude of ds is simply dy. The magnitude of r hat is simply 1, because it's a unit vector. By definition, unit vectors have a length of 1. The sine of theta is just that, the sine of theta. Now the sine of theta, as we look at different pieces of the wire, say if we were looking at a piece down here, theta would have a different value for that piece than it did for the original piece we've drawn. So the sine of theta will be changing. So we need to write the sine of theta in terms of our variable, which is y, before we end up integrating. If you look at this big triangle, the hypotenuse is r, this side is a, this side is y. The sine of theta is the opposite over the hypotenuse, so the sine of theta is a over r. Now it's changing because r is changing. But now we know r relates to y, and so we can write our equation that we need to integrate. Now the magnetic field is a vector, and we talked about finding the direction yesterday. Our ds is in the direction of j hat. The perpendicular component of r hat is in the x direction. So the direction j cross I is negative k. The magnetic field at this point is into the board. And it will be into the board due to any piece of this wire. So since we already know the direction, we can go ahead and just find the magnitude of the magnetic field. So we have mu naught's a constant, 4 pi, obviously a constant. I is the current that passes through the wire. ds cross r hat, we just need the magnitude of it, so it's dy times 1 times sine of theta. But sine of theta is a over r. So the magnitude of ds cross r hat is going to be a over r dy. But then we also have an r squared in the denominator, so we end up with r cubed there. Now we do need to make the substitution that r is the square root of a squared plus y squared. Let's go ahead and pull out the constants while we're at it. So the mu naught, the I, the a are constants, the 4 pi is a constant. That leaves us with 1 over r cubed, but r is a squared plus y squared, to the square rooted, so we get to the 3/2 power dy. Now our limits need to describe the ends of the wire. What I want to determine is the magnetic field due to a very long wire. This will work. The way we have it set up right now is going to work for any straight wire. The limits just need to represent where the ends of the wire are located. So if it was a finite length wire, you would just need to know where the bottom end was and where the top end was. I'm wanting to derive the equation for a very long wire. So basically, my limits are from negative infinity to positive infinity. But if you think about this, if we take a piece up here, ds will be towards the top, r hat is down towards the point we're interested in. The component perpendicular, so this is the perpendicular component of r hat, is in the x direction. So even if we're looking at a piece up here, when we take ds cross r hat, ds is in the j direction, the perpendicular component of r hat is in the I direction, j cross I is still negative k. So a piece down here and its mirrored piece up here will be doing the same thing. So we can actually take our integral from 0 to infinity and multiply by 2, since it's a symmetric problem. Zeros are usually a little easier to work with than infinities are. Okay, so let's see. We can cancel that out. So we have mu naught I A over 2 pi. The integral of this, that's another one on the test notes, the little integral table. In this case, instead of x, we have y as our variable. So the result of this integral is y over a squared times the square root of y squared plus a squared. Plugging in our limits. We're going to run into a problem when we plug in infinity, because we're going to get infinity over infinity. 0 is going to be fine. If we plug in 0, we're going to get 0 over a cubed, basically. So that's fine. The lower limit is 0, but the upper limit. Now, was it called L'Hopital's rule? I can't remember. It's been forever. I just do a little nifty little algebra with it. I'm going to multiply top and bottom by 1 over y. 1 over y over 1 over y is still 1, so I'm not changing the quantity at all. What that does is this y cancels with that one, so I get a 1 in the numerator. I want to bring this y under the radical sign, so I have to square it. So I'm still going to have my a squared there. But when I bring this under the radical sign, I'm going to get y squared over y squared plus a squared over y squared. So that's my inside quantity. Now I can plug in infinity. Y squared over y squared is simply 1. A squared over infinity squared, well, something over infinity squared is going to go to 0. So I still have all this stuff, the mu naught IA over 2 pi. In here, I get 1 over a squared times the square root of 1. So 1 over a, basically. This a cancels with one of those. So this simplifies quite nicely to mu naught I over 2 pi a. So the magnitude of the magnetic field perpendicularly away from the wire, mu naughts are constant. I is how much current is flowing. So how much current is flowing determines the strength of the magnetic field. More current means bigger field. A is the perpendicular distance away from the wire. This equation will give us the magnitude around any very long straight wire. You don't have to derive it again if you have a problem that consists of a very long straight wire.
That's the way you be evaluated.
Yep. Now, in the test notes, we still call that, instead of A, we still call it R, meaning just the radial distance away. So, in here, R means the same thing as A did in our picture. I just didn't want to call it R because that had a different meaning than the R in our original equation we were integrating. So, any problem you have where you have a long straight wire, this will give you the magnitude of the magnetic field anywhere near the wire.